Good morning, everyone. I got some questions. Few students are asking how to start the self-test and do homeworks and things like that. So I decided to put this tape here. Um, Hopefully, it's gonna be helpful. So you open the course, and then you go to the modules. You can also take the left-hand side and you'll be there. So you click the Learn More modules, and this is where we're doing now, Unit 1. So you go to self-test. That's what you want to do. But if you go here, then then you have the exams, right? So you don't want that. You want to first understand what those are all about, and then you want to do them. So again, so you go to modules, find your unit, and open this up here. Introduction to self-test quiz. In fact, certainly would be better to read the chapters, recommended course materials for this unit. Click on chapter 1, and then as you can see, my link probably was posted, yeah, yeah, in the spring, and there is a new version, so you should click here. And then you go to the nature of astronomy, you read that. And then basically in this chapter number 1, it's going to give you an overview of astronomy, all the different things that we are going to be visiting, not only solar system, but stars and universe in large scale, galaxies and clusters of galaxies, and how important space is in all of that. But I would say the core material of chapter 1 is to give an introduction to what exactly science is, because this is a science course. And let me tell you something quickly here. Um, for a non-science major person, the perception people in general have of science is that, oh, scientists, they want to find the truth. This is not correct. This is totally not correct. Uh, the word truth can well be used within the realm of religion. So if you are in a certain religious group or religious faith, there are some statements that are considered to be truth because you cannot change them. If you change them, you're not talking about that particular religion. In science, what we do as far as research is concerned is to negate the statements in existence. In other words, is to negate the hypothesis made to explain how nature works. Ultimately, what a scientist do is to try to explain using the available data, available technology, available network of information to explain how nature works. This is what we do. And when we explain certain phenomena, we come up with statements, with hypotheses as to why this phenomenon is happening the way it is happening. And and then once we establish this hypothesis, other group might start to verify and to test and to create models. And these hypotheses become so complex that we call it theory, especially if the language of science, which is mathematics, is used in a formal way to give consistency to the statement. So eventually, we build up models and theories to explain how things happen. And I'll give a good example: theory of gravity. So the theory of gravity was brought up by Isaac Newton in 1700 to explain how things work. So as far as if you let it go, something's gonna fall. If you look at the moon in the sky right now, the moon is there because of gravity and because of rotation, angular momentum, and it is there the way it is. To explain gravity, Newton came up with a hypothesis. Well, it is due to a force whose intensity depends on the product of the mass of these two objects divided by the square of the distance. So this hypothesis led to make several predictions. You could predict positions of the moon a certain time, when Earth's gonna be a certain time. The whole dynamics of our solar system can nicely be explained by this law. Is this law an absolute truth? Well, history shows us that it's not. And early in 1900, somebody came named Albert Einstein and showed that under certain situations and conditions, this law does not apply. And the example that was brought was light bending in the presence of a strong gravitational field, which is pretty much the sun. The sun was bending the light in a way that Newton's universal gravitational law was not explaining. And then he created not a theory to explain how gravity works. So gravity is due to the bending of the fabric of space-time caused by a presence of a massive object. And it works. It explains everything that Newton's gravitational law explained, plus the bending of light in the presence of strong gravitational field. And so we have this theory now. Is that an absolute truth? Well, maybe one day or a few generations ahead, it will be proving this is an incomplete statement. So science is more about observing nature, creating hypotheses to explain how things behave the way they do, and then we create models. We use the mathematics, which is the formal language of science, to to support and to give logic and consistency to the models. And and more than anything else nowadays, a good theory make predictions of things that you had no idea. So it's unbiased way to foresee the future, if you will, or to predict outcomes. Like um, the finding that collision of neutron stars generate gravitational waves that when it was proposed by early 1900, there was no technology at all to be able to detect these oscillations. Only a couple of years ago, this was effectively confirmed. Okay, so then you're here, you read the book, the chapter book number one, get all excited, and then you go back to your modules, right? It's right there. And I say, okay, I think I'm prepared to do my self-test. Click on it. And in fact, not so fast. So before you go there, I even did something um, cool, which is an introduction to self-test. An introduction to self-test, I do post the slides and the figures that are given in the chapter. And I have videos that I did in previous semester here. So if you want to go ahead of me now, you can go. So I have some videos there. But I will generate these videos every week. And for instance, for self-test number one, the video is here. So as I mentioned previously, just a second. Chapter one is an overview of what is about to come. And it's opening with this nice figure here, two galaxies interacting and colliding. In fact, in our observatory, we try to take a picture of these galaxies and then these two galaxies colliding. And then we realize we have to improve our technology because the image was not so good. We could see a blurb here and another blurb there, but not so much. But so galaxies are complex structures with hundreds of billions of stars, plus so many gas that is able, each star is able to harbor its own planetary system, and and we are going to study this in about 1 month and a half. In our solar system, you have planets, you have dwarf planets, gas, zodiacal gas, comets and asteroids, and the sun, of course, where most of the material resides. Here's a picture of Mars. We are not going to invest a lot of time in planetary science. We are not going to study in details what type of interior these planets have and what type of atmosphere, what exactly, uh, how they formed, and all these details. This is more for a course on solar system, and we don't have that yet. Now, gas is the ingredient that forms stars. So stars, they come and go. They have an importance presence in our universe because they are the luminaries. I mean, we see things and we can take pictures like this picture here that I'm showing. It is possible because there are stars in it, and light produced by stars is being either scattered or reflected or emitted out of gas, and then astronomers can go ahead and take picture. So again, in our galaxy, in our Milky Way galaxy, there is gas out there, and if the conditions are just right as far as gravity is concerned, gravity will start collecting this gas in clumps, and out of these clumps, a star system will be formed. And we are going to study this as we go. This is another picture of a beautiful nebula, Orion Nebula. We can see in our observatory, probably not right now, and um, all this bright, beautiful nebulosity here comes from a bright star. It's a single star that illuminate all of that. Is a O star, and we are going to learn that um, in probably, you know, yeah, about 2 months. And this O star is a hot star, produce a lot of ultraviolet radiation that is able to light up this gas over here. Now, telescopes are the or constitute the instruments astronomers use to collect the light and bring the light to a point where not only professional astronomers but students also can infer properties of celestial objects. And so telescopes is more like a tool. We don't know things about quasars, galaxies, and whatnot just by observing, like in the 1800s. Late 1800, astronomers would go to the eyepiece and look at a galaxy, the image of a galaxy, and draw and try to um, make conclusions. So nowadays, the two major tools astronomers use to unveil properties of celestial objects are spectroscopy and photometry. So you need a telescope to collect light, but then you need a lot of hardware and other components and optical systems that allows astronomers either to count the number of photons, particles of lights, or to measure the intensity of the source that is being observed, or astronomers want to take this incoming light and spread out in a rainbow and study um, this rainbow in fine detail, enabling them to determine not only the chemical composition of the celestial objects, if they are rotating, if they are rotating fast or slow, if they are coming towards or away from us, and that is what spectroscopy allows astronomers to do. It's one of the most technical subjects we are going to be studying, but it's fundamental in order to give us, students and professionals, the certainty that what we do is scientific. You don't need to go to quasars to collect a piece of quasar and bring to the laboratory like we do it with other sciences. In other sciences, we go to the laboratory and we dissect the object of study and we do all of that. In astronomy, we can't we can't bring a piece of galaxy to our observatory or to our laboratory. So what do we do? Well, we know how light behave. We know how light interact with matter, and we know what fingerprints this interaction put in light itself. And then we spend 2 or 3 years of our academic life learning what those fingerprints represents, and the rest is just having fun time doing science. Is now our blue beautiful planets and the Earth and Moon scale. You see how empty the solar system is. And when we draw the solar system as a crumble representation with one circle representing the sun and a few others representing planets, it's a disservice to learning because we are not representing reality what the solar system is. Solar system is a vast system and yet very small when compared with the entire universe. That's why astronomers use units like astronomical unit, which is the average distance of Earth to the Sun, or light year, which is the distance. A light year is not a unit of time, but it's a unit of distance. Is how far light travels in a year. One example, Earth has a diameter, right? So the distance of Earth to the Moon, you could say, is 30 Earth diameters. So if Earth is represented by a soccer ball, you have to come up with 30 soccer balls, one next to the other, and at the end of the 30th soccer ball, you place a little, uh, probably baseball, quarter size of a soccer ball, and that is the Moon. So that's why eclipses are not so frequent. You have a seasons for eclipses every 5 months, and we are going to study that. So the sun is how far the sun is from us. Well, the sun is about 8.3 minutes light minutes away from us. So once the sun emits its speckle of light, that light takes 8.3 minutes to arrive here. So if the sun disappear right now, we won't know up to 8.3 minutes later. So for instance, this is not in scale, right? That's what I just said. It's not a good representation of what the reality is. Earth, the sun, for instance, is can in its diameter you can put about 10 Jupiter one next to the other, and Earth is 1/10 of that. So 100 Earths can go in in one solar diameter. Here's a picture of spiral galaxies. Stars forms in associations, in groups. Long time ago, when our galaxy was formed, globular clusters were a nice avenue for star formations, and they would form in clusters of hundreds of thousands of members. And this is a picture of galaxies and clusters of galaxies. And that's how a universe in large scale happened to be organized. So key points of chapter 1, scientific method. You observe, you create an idea, and that idea has to be testable. For instance, in science, I cannot discuss God or angels. This is not part of the communication. We cannot put that in a paper because I cannot summon God in the laboratory or the angels and describe their properties in a way that in other laboratory colleagues can reproduce that statement and test that statement. So we can only use in our hypothesis, in our explanations as to why how certain phenomena occur, we have to we have to use elements that can be tested. And again, as I said in the very beginning, science is not a search or a path to find the truth. It's a path to negate the statements in existence. Is a way to negate what we think we know about reality. Is maybe that's what makes science so exciting, because it's a non-ending process to understand how nature operates. And also a key point in this chapter is the scale of the universe. Again, if you need any question, don't hesitate to email me anytime. All right, have a nice day.